Hello everyone, welcome to the InThink channel. In today's video, we will test and disassemble this device to understand how it works. It's an electronic pedal. I bought this one from China, and it can have many applications, such as in electric scooters. It can also be used in any equipment with a motor that you want to control through the pedal, right? It operates with 3 wires: the power wire, red, the negative, yellow, and the output, green. These colors may vary depending on the manufacturer of the pedal. An important point to highlight is that some pedals work with potentiometers, which tend to get damaged quickly due to frequent actuation during use. To solve this, they use a linear Hall effect sensor inside the pedal, which provides much greater durability since potentiometers are mechanical parts that wear out over time from the friction caused by repetitive movement. First, we will perform a test to connect the power and check the output signals of the pedal. We'll use a multimeter for this. We'll measure the output from the connector and wires. We'll also need a power supply, like this one I have here, a USB power supply with an adjustable potentiometer. I've already connected and set it to approximately 5 volts, and the multimeter shows exactly 5 volts. I connected the black probe to the sensor's negative wire and the red to the connector that's already wired to the power source. An important point when talking about voltage of power supply, the advantage of the most Hall effect sensors is that they have a wide operating voltage range, from about 4.5 volts to 24 volts, depending on the equipment that will receive the sensor's output. Now let's connect the sensor to the pedal. When measuring with the multimeter, we see that with the pedal at rest, the initial voltage is about 0.86 volts, which is normal when the Hall effect sensor is subjected to a magnetic field. When pressing the pedal, this voltage increases gradually until it's close to 4.14 volts, a bit below 5 volts, which is the supply voltage. We also tested with a 12-volt power supply, where the initial voltage rises to about 0.9 volts, and pressing the pedal causes it to increase up to 10.2 volts, showing that the higher the supply voltage, the greater the amplitude of the output signal. Inside the pedal, the mechanism operates with linear motion, with the Hall sensor positioned so that pressing the pedal causes the magnet to move in front of it linearly. Now let's open the pedal to view the electronic parts. There are 2 pins holding the cover, along with 4 screws we need to unscrew. Inside, we find 2 springs that return the pedal to its original position, and the linear Hall effect sensor, which is model 49E. This sensor works with magnets and needs to have a magnetic field with half the pole south and half the pole north. The magnet is mounted in the cover and is positioned directly in front of the Hall effect sensor. One half of the magnet is magnetized with south polarity, while the other half is magnetized with north polarity. When the pedal is pressed, the magnet moves in front of the Hall effect sensor, changing the magnetic field. This variation generates a corresponding voltage output in the linear Hall effect sensor. Now let's test the linear Hall effect sensor. I am using a 12 VDC power supply. As shown on the multimeter, the sensor output is approximately half of the supply voltage because there's no magnetic field directly in front of the sensor. This corresponds to the central region of the magnet, at the boundary between the north and south poles. By adjusting the Hall effect sensor supply voltage to 5 VDC, it is possible to observe that the output is reduced to approximately 2.35 VDC, which corresponds to half of the supply voltage. When the cover with the magnet is mounted and the pedal throttle is in the idle position, the magnetic pole facing the Hall effect sensor is the north pole, resulting in an output voltage of approximately 0.8 VDC. So to test, let's use this round small magnet. This one has the flat surface as the north pole and the concave surface as the south pole. When the north pole of the magnet is positioned directly in front of the linear Hall effect sensor, it is possible to observe that the output voltage drops to approximately 0.8 VDC. To confirm this, using the pedal magnet, we can observe that the region of attraction with the south pole of the rounded magnet corresponds to the north pole region of the pedal magnet. We can also observe that the north pole of the rounded magnet is attracted to the corresponding south pole of the pedal magnet. In the magnet, we have, at the extremes, the magnetic field is strongest, one end corresponding to the south pole and the other to the north pole, while near the middle of the magnet, there is almost no magnetic field. When the concave surface of the rounded magnet is positioned in front of the Hall effect sensor, the multimeter reading increases to approximately 4.1 volts. So, to summarize, when the sensor faces the north pole, area of no magnetic field, the voltage reading is close to 0. When the magnet approaches the south pole, area of stronger magnetic field, the voltage approaches 5 volts, or the supply voltage. The linear Hall effect sensor provides an analog output, different from bipolar or unipolar digital sensors that have digital output, 0 volts or VCC. Therefore, the output voltage varies depending on the magnetic field. To summarize, as the magnet moves in front of the sensor, the output voltage varies linearly between about 0 volts, north pole, and near 5 volts, south pole. So, pressing the pedal moves the magnet closer to the sensor, generating a voltage proportional to the linear motion, which can be used for speed control or position sensing. Thanks to everyone who stayed until the end. If you liked the video, leave a like and subscribe for more content like this. See you next time.